Okay, so let's move on to the next bit that we're going to talk about. This is actually chapter 6, so we're walking backwards in your book. Chapter 6, acid-base reactions. Acid-base and donor-acceptor. Chemistry. So in this section, we're going to talk about like acid-base interactions, which you guys know pretty well. We're going to talk about donor-acceptor chemistry, which is a bit different. And if you remember, like maybe from Gen Chem or like analytical, you might see like a structure like this, where it's a transition metal complex.
Copper transition metal.
Like that.
Oh, no.
So what do these bonds mean? How does this happen? We're going to talk a little bit about that, or at least how to lead into that sort of stuff. Okay. So before we do that, we need to talk about acids. So we need to talk about Lewis acids and Lewis bases. What's a Lewis acid? What's a Lewis base?
Lewis acid is an electron pair donator.
Other way.
Acceptor.
Yeah.
Close.
Electron pair acceptor. This is the electron pair donor. Okay. And the bond that links them together is known as a dative bond. A dative bond.
I feel like we learn this every class of chemistry.
Oh, yeah.
It's a really important topic.
Organic.
But I still don't really know it.
Oh, shit.
We're gonna beat that. Don't worry, we'll get that. So I truly didn't understand it until my inorganic class. I just did it on like for organic. I memorized everything. I did organic the completely wrong way of just memorization. You really should learn the rules and the ideas behind it. I didn't. And I really didn't get it until I started taking inorganic and another course called organometallics, which was my like favorite course in college. So
it's a
Dr. B
dative
is favorite.
bond.
What kind of bond is it?
dative.
Dative.
Yep, we'll talk about what it is. We're going to show it in just a second. So let's look at Lewis acids and bases. And frontier molecular orbitals. So does everybody know what I mean by frontier molecular orbitals?
No.
Like the outermost one?
Yep. So basically like the HOMO, the LUMO, highest occupied molecular orbital, lowest unoccupied molecular orbital, and maybe some around those points. So let's look at the interaction between boron tetrafluoride and ammonia. So consider reaction of BF3, and what's the formula for ammonia again?
NH3.
Yep.
You go,
Okay.
girl.
Let's draw these things out, or at least some Lewis structures. Whoa, except I'm forgetting bonds. Okay. They're going to react and something's going to happen. Can anyone tell me what's going to go on?
NH3 is going to take, no, BF3 is going to take an H from NH3.
That is a possibility you could think of, but then you get an NH2 minus, which is
Yeah,
really
it's gonna be
energetically
NH4
unfavorable.
plus is what you want.
Yeah.
So
Any
what-
other ideas?
You could take those electrons on the N and you could throw them over to that B and then get rid of
Or
it.
then they're gonna make it complex.
Yeah, that's exactly what happens. So
My sister's insane.
H, and I'm forgetting something on here. What am I forgetting on this Lewis structure?
Normal charges.
Yep. What's got to go here on that boron?
Minus.
Yep. Nitrogen.
Plus.
Yep. And this guy right here, that's the dative bond.
50-50 shot.
There you go. Okay. So now let's look at the molecular orbitals and let's see what's going on here. And I bet you guys can actually tell me what's occurring. I'm going to move this up a little bit. Okay. So we're going to ask question, what about their MOs? We're going to plot, we have energy on this axis. We're going to have our two fragments. We're going to have BF3, NH3, and then we're going to have BF3, NH3, like that interaction. Okay. So now let's try and guess what's going to happen. Which one of these compounds was behaving as a Lewis acid? Which one was behaving as a Lewis base?
The acid was the BF.
Yep, the BF. Yep, this is the acid, Lewis acid. And that leaves the ammonia to be the base, right?
Right.
Okay. So now let's think about their frontier molecular orbitals. It's usually the HOMO and the LUMO of two molecular entities that interact with one another to form a new bond. So is it going to be the HOMO or the LUMO of the boron tetrafluoride that interacts with the HOMO or the LUMO on the ammonia? So again, what does the HOMO means highest occupied molecular
The
orbital, right?
HOMO of
The
the
HOMO
NH
of the
goes
B.
to LUMO
NH3.
of the BF.
What were you saying, Maddie? I'm sorry.
The HOMO of NH goes to LUMO of BF.
Yep, exactly. So John, is that what you were saying? And Josh?
Yeah, we kind of all started talking over each other.
Everyone gets excited. That's awesome. It's good. Okay, yep. Maddie's right.
Mark it down.
10:25.
Go second at 10:25 a.m.
In this day in history,
Yeah.
and these guys interact with one another. And now, where there was no bond, like there was no interaction there, there's now a new interaction. Now, what does that mean about the charge? So we drew up here, what happened to the electron density? It went from the nitrogen to the boron, right? So what's going to happen in this case? Or how do we know charge is going to go to that BF3 based upon this drawing?
It's lower in energy.
Lower energy, yep. And this portion right here, remember from the LCAO, or the linear combination of atomic orbitals, these orbitals themselves, this one only has ammonia character, this one only has boron tetrafluoride character. What about this new hybrid MO? What type of character does it have?
Both.
Both.
Yeah, it has both. So this new hybrid MO forms. that now has character of both boron trifluoride and NH3. And since the boron trifluoride had an unoccupied orbital that was contributing to this, it now gets some charge. So since BF3's MO was unoccupied, it acquires some charge. Electron density, I'm going to say. And that means the NH3 loses some charge, right? Okay. Let's see. Let's look at one more instance of this. Am I okay to pull this up?
Mm-hmm.
Go for it.
So let's ask the question, how does H2O interact with calcium solid? Anybody know how that works out?
I'm guessing it could like dissolves it.
It
Isn't
dissolves
it,
it.
Isn't there like a combustion?
Yeah,
does it
it's
make like calcium hydroxide, or is it?
yep. It's going to make calcium hydroxide. It's a combustion too. Well, it creates hydrogen gas, and it's so hot that it actually burns that off. So 2H2O liquid plus calcium solid, calcium 2 plus 2 hydroxides, and H2 gas. Actually, at the place I worked at before Bana's, I was there late at night one night because for once my wife and I drove separate. We would drive into Allegheny County together, and we wouldn't talk to one another along the way because I'm super grumpy in the morning and hate talking.
Okay.
So, but I was there late, like about 9 o'clock one night. It just happened to be a random time we weren't driving together. And we had an adjunct that was working for us, and she dropped a bottle of calcium on the floor. And calcium is covered in mineral spirits. What she was doing is she was picking the stuff up by hand and trying to scoop it into another jar full of water. So she had chemical burns all over her hands. Luckily, I stopped her before she dropped it in water. Can you guys see why that would have been a bad idea?
Like, how big of a chunk are you talking about? Because
I'm
calcium's
talking about,
pretty
like,
reactive on the scale of
about
reactiveness.
turnings, a group of turnings the size of my head in a jar. So she wanted to take that, throw that in a jar.
What was her job title?
She was an adjunct instructor of chemistry. She taught like I think she taught something like biology or I don't know. That's why it's always you want schools to not have adjunct professors, not because they're bad, but just because they don't get enough training. That's the biggest point. Okay, so let's look at this MO interaction.
I wish I could have seen your reaction. You like yelling
Oh,
at me.
I freaked out. I was like, "What are you doing?"
So she doesn't even have gloves on, nothing, just, oh, let's pick it up by hand.
Yep. I couldn't believe it. I was impressed. Okay.
That would
We're
be
gonna
weird. Even after the story.
Yeah, it's getting me going still. All right. So
Josh, you're back.
I am back. Yeah.
I was just getting used to Jacob.
Jacob figured out how my laptop was on, so
how to make it work.
Yeah,
What a guy.
We love Jacob.
good guy.
It'd be like that.
From time to time.
So now, let's look at this guy. Tell me from this reaction what's going to happen. Looking at those MOs.
The calcium electrons are going to come down to the LUMO of
Mhm.
H2O.
Yep, so basically what happens is these guys get donated to there. If you look at their hybrid MO, what ends up happening is that doesn't change much in energy. So it's basically just H2O in character. Now this is an anti-bonding MO. The way that this anti-bonding MO looks like is this that has a bonding combination there. And it looks something like that. Looks like I don't know, a person in a dress with a funny hat, I guess. Okay, so what's going to happen to the HO bond length as we populate that LUMO? That's the way the LUMO looks. So what happens to the HO bond length as we start populating this LUMO?
Increases.
Yeah, it's going to increase. So what happens is electrons are transferred to this LUMO. It increases this bond length and it actually ruptures that bond. And you get this interaction that occurs. So electrons are transferred. Oh, there we go. From the calcium 4s to the water LUMO. And since this LUMO is anti-bonding, it weakens an OH bond. And that leads to that H2 gas. There are other examples that are given in your book of these interactions, and you can look at what happens to the frontier molecular orbitals. I highly suggest to read that through so you can get an idea of what that looks like. But I want to talk about another topic before the exam, and it's one that I've always wondered why we just don't teach in general chemistry, but we tend not to. Let's talk about the solubilities.
So we have another inorganic exam next week.
Yes, I think is it on
Okay.
Tuesday?
Sounds right.
Or is it on, yeah, we'll look that up right now. That's important to know. That's syllabus. Got syllabus modified. Let's see. April 7th. Yep. So, yep, next Tuesday.
5 days. Yeah, that makes sense.
Solubility. Do you guys remember all those solubility rules that, I don't know, some professors might have forced you to memorize? Not me. I always had them on the back. But you know those
There's a
solubility.
chance, man.
Like, if you start throwing some things out there intuitively, maybe.
Oh,
Everything like group 1 and group 2 is soluble.
right. What about silver nitrate? Soluble or insoluble?
No, silver is not soluble in this.
No. But what about nitrates?
Oh, nitrate is? Is that rule like over counter this?
Oh, is that like the one exception of so?
Yep, that's soluble, but like AgCl, not soluble. It's solid. Have you ever wondered why those rules come about? Like why, like, okay, yeah, experimental observation, but inherently, why is it this way? That's what we're going to talk about. We're going to talk about hard and soft acids and bases. So hard and soft acids and bases, what you're doing is you're considering the polarizability of the anion and cation and how it influences solubility and its equilibrium. So considers polarizability, relationship to solubility, and equilibrium. Okay. If the compound, or excuse me, if the ion or metal is easy to polarize, it's considered soft. Non-polarizable, it's considered hard. Now, do people get what I mean by by polarizability?
Yeah.
Yeah. So what, can anyone tell me what polarizability is?
It's the, like, how hard is it to make the electron density move of
Yeah.
the certain molecule?
Yep. So if we have this, and that's our electron density, if we apply an electric field in the Z direction, or you guys like the Y direction, like how much will it do that?
What is that written about the arrow?
This, that's epsilon.
Oh.
And you usually use that to denote an electric field.
Okay.
And that's just telling us what direction the electric field is being applied. Okay. You can look in your table and you can see a table and tell us something is hard or soft, but we're going to go through and we're going to pick a couple of these acids and bases, and we're going to decide if they're hard or soft. Okay? So let's talk about hard and soft bases. We're going to make a table. We're going to have hard. We're going to have intermediate. We're going to have soft. Okay. So let's consider the halogens. So I'm writing on another sheet of paper. You don't have to write this down yet, but just so if you can't understand what I'm asking.
It would be hard.
Cl minus.
This is it's a weak conjugate base. I know that.
So it's a weak base. Where's
So
it
it's
going
probably
to
soft.
actually? So it's a weak base,
So-
right?
So that means it's probably hard to polarize.
Yep. Hard. What about F minus?
That's soft.
That one's
Or
soft.
intermediate, probably.
Well, it's
Intermediate, because it's technically not a strong base.
So does it like to polarize?
Yeah, it's not stable, so it wants the electron.
That is true. It usually wants electrons, but is it easily polarizable?
No.
Is it harder
It is
to
all
polarize
hard.
it than Cl, technically?
It's harder than Cl because remember, this is one that has a really high effective nuclear charge. So it's going to pull in that electron density really tight. What about, I don't know, Br minus?
Probably hard as well.
Starting to get easier.
It's
Easier?
easier. We're going to put this one in the intermediate. What about
Just do those size.
I minus?
It's Go soft.
Probably soft.
Yeah.
I don't know. What was it?
Yep, it's soft. It's big. There's a lot of electrons, easy to shuffle around. Okay, let's ask another one. Let's ask H minus.
Hard.
Hard, soft, or intermediate?
Hard.
Is it
Or technically,
easily-
that's a love to donate its electrons, so wouldn't it? No.
Right. So does it hold on to that extra electron very efficiently?
No.
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 No. So does that make it hard or soft or intermediate?
It would make it soft
Probably.
if it wants to give them.
Super soft. 10 ply, bud.
Okay.
There we go. Letter Kenny shout out. Yeah,
10 ply. I got that. Yeah, I got that. That's good.
you're 10 ply, bud. All right.
I've
Love
like
that
barely
show.
watched that show, but
That's
it's
actually one of
it's
my
great.
favorite insults from that show.
You know, yeah, probably 10 ply.
Okay, let's consider OH minus. If you had to put OH minus somewhere on here, where would it be?
Probably soft.
Is it easily polarizable? We got one vote for soft. Anyone else?
I'll go hard. Why not?
So we got 1 and 1. Tara, Maddie, we need your help.
I can't choose between my JoJo's.
Soft.
Tara, can you? Nope. She's remaining silent.
You could have chosen intermediate, and you'd have to join us if you want.
Yeah.
This one's actually a hard.
Yeah.
Oh,
So this
Hey.
doesn't really have to do with like strength of base, or does it?
It's not.
It's
Remember,
not
strength.
linear.
When we're talking about strength of acids and bases, we're talking about their ability to dissociate, not necessarily the reactivity. HS minus. Is it going to be harder or softer than OH minus?
It would be
Softer.
softer if it's
Right.
going to follow the trend of the halogens.
Yeah. And that makes sense, right? Because if you think about the polarizability of these ones, they're more polarizable as you add more electron density as you go down. Okay, let's ask, let's see. Let's write just a couple more of these out. These are ones you'll want to look up and know a couple of them, know trends between these. NO3, 4 minus, N2, azide, thiocyanate, cyanate, RCN, like that, carbon monoxide. So those are some examples. Let's look at acids. Am I okay to move this up?
Oh,
Is
could you
that
actually move
CO
to the
minus?
left just a touch?
That's
Yeah,
just
let's
carbon
do the last
monoxide.
one.
I'm
No.
sorry, what's that, Josh?
Oh, sorry. Does that just say carbon monoxide itself is a solid?
Yep, carbon monoxide. Yep.
Okay.
Yep. Okay. If you look in your book, there's a table, has a bunch of them.
The regular book or the other book?
The inorganic book.
Okay.
Yep. It's somewhere in this office.
Shouldn't that say acids?
It should say acid, sorry. Hard and soft acids. We're going to do the same thing. Hard, intermediate. And soft. Okay. So now for this one. H plus. Where do you think that's going to lie in the spectrum?
Let's go
It's
It's going
soft
to
again.
be very hard.
Yep,
Very
this
hard.
is very hard. Why is this one of the hardest acids?
Well, because there's no
Does not
really
really have any electron density.
so it can't really be polarized.
Yeah, exactly. It doesn't have any electron density. Can't be polarized. This guy's hard. What about like Li plus?
Still
That was
probably,
probably pretty hard too.
Yep.
yeah, but
Let's say sodium plus.
I'd say that's intermediate.
It's still considered hard, but it's less hard than like lithium.
Yeah, okay.
gotcha.
Na plus.
Is it following a linear scale here, or is it like exponentially dropping off as you're going down?
It depends.
Okay. Always.
Yeah, yeah. I can't give you a straight answer on that one. K plus. What do you think?
Let's go intermediate.
No, that one's it's still considered hard because they're not really well polarizable. Let's go with, oh, I'm covering that up. Let's go with the beryllium 2 plus. Where would you throw that guy?
It's
Still hard.
hard.
Yep, still hard.
Are they all hard?
Pretty much. So like magnesium, calcium 2 plus, strontium 2 plus. Okay, let's talk about some of the transition metals. So, some intermediate transition metals, and the oxidation state does matter. An example of those would be like iron 2 plus, cobalt 2 plus, nickel 2 plus, copper 2 plus. If you had to think of a soft metal, could you give me an example of a soft metal?
Lead.
Yep, lead.
Like in characteristic, or like
Yep, lead. Where is it?
or something.
PB, yeah.
Yeah,
It's 82
let's see.
or
I don't actually see a spot for lead. So let's
How
think
about tin?
lead should be soft, I would say. What was another one, Josh?
gold.
Tin?
Yep, gold 2 plus, or actually gold just plus, I'm sorry. Tin.
Oh.
Let's see. SN. I don't really know where tin would lie.
Huh. Okay.
I think that one would be a bit harder, but I don't know. Since we have silver, or gold, we also have silver, cadmium 2 plus. If we look at some harder metals, that'd be like chromium 3 plus, manganese 2 plus, iron 3 plus, cobalt 3 plus. Oh. Now, let's look at these. Iron 2 plus is considered intermediate, but iron 3 plus is considered hard. Why is that? Or,
Like,
yeah, John, what were you going to say?
so it's just that it's giving up electrons more and more, so the atomic charge is pulling everything in closer.
Yep, exactly. And what happens to its polarizability?
It would decrease as you pull more electrons away.
Yep,
So it becomes
exactly.
harder. Yeah.
Making it harder. So, ions with high oxidation states. Would be considered more hard, where what would you put for metals if we wanted a soft metal?
Low oxidation state.
Yep. There are many more hard and soft acids that we're not indicating on here, but just know those general trends of where, think about that polarizability and consider what's going to happen. All right, now let's put this into practice. Am I okay to move this up?
Yep.
So, example, we're going to bring back some analytical in here from Gen Chem.
Never been there.
Write out all the KSP expressions for the following and determine the trend going down the periodic table. So we have AgF solid, Ag plus, F minus. We have AgCl solid, Ag plus, Cl minus, AgBr solid, Ag plus, Br minus, and AgI solid. Okay. So we have all of these silver salts. We're going to throw them in solution. We're going to let them reach equilibrium. I want you guys to tell me each of the KSP expressions, and then we're going to go through and we're going to determine which one will have the highest KSP, which one will have the lowest KSP, using hard soft. Okay. All right. So blast from the past, trying to recall these KSP expressions.
Isn't it just Ag plus times F minus?
It's products over reactants, right? So what
That's a
about this guy?
solid.
Yeah, there you go. Got him. And what do we know about, what do we know about solids?
We don't care about them.
Yeah, we don't care about them. And why, does anybody know why we don't care about them or remember why we don't care about them from PChem?
Because their value is so close to like 1, or it's something that's like so big that it could be just not looked at, or so small.
Yeah, it's not changing. Also, if you look at that chemical potential, the chemical potential for a solid or a pure liquid doesn't change. Okay.
Email Evanowski Cole. Tell her I did good.
Yeah. We miss her.
Yes.
So what's the KSP expression going to look like for all of these guys then?
It's the same thing, just a different halogen.
Yeah. Just different anion. Ag plus, Br minus. Oh, I minus. Okay. Now what we have to do is we have to determine which one will be the most soluble. And what was the relationship with KSP? As KSP increases, what happens to solubility?
Increases.
Yep. Because this expression gets larger, that means there's more of this in solution. Okay. I probably shouldn't have written that there. Dang it. Okay. Which of these do you think is going to have the highest and which do you think is going to have the lowest? And remember, try to go back and consider the hard, soft acids that we have. So first thing we want to look at is where does silver plus lie? Is it hard, is it soft, or is it intermediate?
It's gonna be soft.
Yep. Ag plus is soft. Now we know these guys. We know, okay, F minus is hard, Cl is hard, Br is intermediate, I is soft, right? Now, soft ions mix the best together. They form the strongest interaction. Whereas if you have a mismatch, you have like hard, soft, they don't have the best interaction. So if you have two hard hards meet up, that's good too. Okay. So what do you think is going to happen? Which one's going to have the highest value of KSP? Which one's going to have the lowest value of KSP?
Highest is gonna be with the
AgI negative.
What'd you say, Tara?
the highest is gonna be with the I and the
Mm-hmm.
lowest is gonna be with the F.
Yep. John, is that what you were saying?
Yep.
Okay. Yep, that's exactly right. So this guy. Wait, did we say the highest was going to be
Yeah.
which one?
I.
Yeah.
Remember, this is the most soluble. That means this bond is least favorable.
No, you said that because they're both
Whoa,
soft.
whoa, whoa.
Right, I said they're both soft, so they make a stronger bond, right?
Yeah.
So which side of the equilibrium is more favorable?
Wait.
This
You
side,
said that it makes it a better bond if they're both soft?
if they're both soft. So, Tara, which side of
Okay.
the equilibrium is favored if it's making a strong bond? The left or the right?
The left.
Yep. So this is favored. So what does that mean happens to KSP?
KSP is really small in that case.
Yeah. It's going to be small. I'm sorry, I lied to you.
Yeah, because you kind of said something else
So
about
because,
it being the
so
highest.
because iodine is
You led us
soft,
astray.
oh wait.
I'm
So because-
10 minus 13.
So with both being soft, you get a really unsoluble, but both being one hard, one soft will make it much more soluble.
Right. So if you have soft, or hard, that's more energetically favorable. Whereas if you have soft, hard, or hard, soft, that's unfavorable. So like I said, if you have two entities that are soft or you have two that are hard, they're going to form a stronger bond, right? And because that bond's stronger, that means this side of the equilibrium is favored, meaning they're less likely to dissociate, right? So that's why these start to decrease as we go down. Does that make sense? Okay. So now we're going to ask another question. This is very representative of a multiple choice question you may see on an exam in your near future. Am I okay to move this up?
Mm-hmm.
Go for it.
Example. Which is the least soluble? You have LIBR, LII, LICL. I'm sorry, I should say least soluble in water, but we're going to imply that. We have these guys. Okay. So we're trying to figure out which one is the most soluble, or excuse me, the least soluble in water. We want to consider which will have the strongest bonds, which will have the weakest bonds. So
Probably
which of these?
LIF.
Yep, LIF, strongest bonds. Why'd you go with that one having the strongest?
It's a hard
Yep.
relationship, and with
one-
fluorine being the hardest, and the halogens are the most polarizable.
Yep. This one is also hard, right?
Or, I mean,
What about this guy?
hardest to polarize.
So
That's a hard
LIBR,
soft.
yep, hard, soft. And this guy, LI, is also hard soft, right? Okay, so that one has the strongest bonds. Which one has the weakest bonds?
LII.
Yeah. These both have pretty weak bonds. Okay, so now we have to consider solubility. And remember, solubility is the ability to dissociate in solution. So which of these has the lowest ability to dissociate in solution?
LIF.
Yep, LIF. The bonds are the strongest. They want to stick together. They don't want to break apart, right? So this guy is our answer. It's the least soluble. Does that make sense to everybody? Okay.
So which one would be the most soluble in water?
If you look at experimental evidence, it's actually this guy that is the most soluble. These two are close to one another, but is there a reason this one might be more soluble than that guy?
So have to deal with their atomic orbitals and whatnot.
Yeah, and their weight actually too. So
Stuff always gets weird between those two.
yeah, exactly. There's also relativistic effects that happen for iodine because it's so heavy. That could also be a reason. I don't know if that is, but it could be. But if you, on an exam, if you were to guess either of these, I would give you credit for that. Okay. Any other questions? Okay. One more thing I want to emphasize. When considering the transition metals, why do the metals with less d electrons tend to be hard? So when we look at those transition metals and we have ones with less d electrons, why do they tend to be harder?
Because in comparison, if you have more d electrons, any bonding overlap with the d orbitals is going to be not as good as many other overlap or bond.
That could be true, but I want something more basic than that. When we're talking about hard and soft, what are we really discussing?
The polarizability.
Polarizability. So why does it make sense that less d electrons, what's going to happen to the polarizability if we have less d electrons?
Harder to polarize because there's less electron density in the first place.
Right. So less polarizable. And kind of keep that connection of hard and soft having to deal with polarizability. Okay. We're going to ask one more question, and then I think we'll be done for the day because we're going to talk about something else that's completely different next time. Okay. One more question. Is OH minus or S2 minus more likely to form an insoluble salt with a 3+ transition metal ion and then we're going to ask what about a 2+ transition state? Or I'm sorry, transition metal. I don't know why I'm saying transition state. Transition metal ion. Okay. So if you had to pick, is OH minus hard or soft?
Hard.
Yep, it's hard. What about S2 minus?
A little bit softer.
Yep, it's actually considered soft because it's just a negative anion hanging out there. All right, now if you had to place these transition metals, which one would form an insoluble salt with a transition metal that had a 3+ charge? Would it be
Due to
Would be OH.
but yeah, because they're both hard. Or no, wait. Yeah, both hard.
Yeah, hard makes something insoluble.
so hard makes something insoluble, right? So if we go back to this, so we look, you guys said the 2+ were intermediate, right? And the 3+ were hard. So what's going to go well with the OH then?
Hard,
Uh,
another hard substance, 3+.
Oops. There we go. 3+ metals. Or S2 minus, that'll be 2+ metals. All right. Okay, we don't really have enough time to do the next portion. Is there anything you guys want to discuss from today's class? No?
Ooh, still gotta make my cheat sheet for tomorrow.
I'm sorry, what was that?
Nothing. I just gotta make my cheat sheet for tomorrow.
Yeah, get your pecan stuff ready.